Welcome, everyone. It's good to see that everyone got in, so we can start with the program. We just heard an excellent ITC colloquium, a brilliant one, by Adrienne Erickcek, and she's visiting us from Chapel Hill, and she will say a little more about her recent work in a few minutes. We'll start with Jasleen Matharu from Cambridge. Tell us about the cluster versus field stellar mass size relation at redshift 1. And then we'll continue with Adrienne, and she will tell us about observational signatures of the Kination. All are anticipating to understand what that means. And then we'll hear from David DeVorkin, historian of astronomy, he's sitting over there, visiting us from the National Air and Space Museum. And he will talk about a new exhibit at the National Air and Space Museum, how to highlight theory and computation, which is very dear to our hearts. Even though
get your attention.
Some of our best friends are observers. And then finally we'll hear from Christina Eilers, visiting us from MPIA, about how do supermassive black holes grow in the early universe.
Okay. Hello everyone. So I'm from the other Cambridge, and I've come to visit this Cambridge to tell you a bit about what I've been doing in my PhD project. So first of all, to start off, in general, galaxies grow in size via mergers. That is, galaxies at higher redshifts were smaller and they merged with larger and larger systems to create the large galaxies that we see today. And this can be seen more clearly in the stellar mass size relation of galaxies shown here on the left for different redshifts. And the mass size relations are shown as the solid black lines. And in general, you can see there is a trend of the intercept increasing when we go from high redshifts to low redshifts. And this is more clearly seen in the size evolution at fixed stellar mass here. And you can see that both star-forming and quiescent galaxies rapidly grow in size with redshift, but the quiescent population grows much more rapidly. And there's been two ideas for what could cause this rapid growth in the quiescent population. The first idea is this idea of minor mergers. And minor mergers are basically mergers between two galaxies that have very different stellar masses. And the idea came about when observations showed that the number density of compact quiescent galaxies reduced dramatically below a redshift of 2, suggesting that these galaxies must have grown in size for this dramatic reduction in the number density. Further observations showed that the stellar densities of high redshift quiescent galaxies actually matched the stellar densities of the inner regions of the ellipticals we have today in our universe, suggesting that these galaxies have somehow puffed up their size without increasing their stellar mass very much. And it's been shown that minor mergers can increase the size as stellar mass squared. However, the other idea of what could cause this rapid growth in the quiescent population is the idea of recently quenched galaxies. And this came about from observations showing that the number density of compact quiescent galaxies doesn't actually change very much with redshift. What does change is the number density of large quiescent galaxies at later times, suggesting that these galaxies are actually responsible for increasing the average size, not the growth of compact quiescent galaxies. So for a while there's been a debate on which of these processes actually dominates. Are they both happening? And to complicate this whole thing even further, you have the problem of environment in galaxy evolution. You have clusters in which satellite galaxies are moving very fast, and you have mergers being rare, and then you also have the field environment where galaxies are moving more slowly and mergers are likely. But in this scenario, you can actually exploit environment to test the minor mergers hypothesis of size growth because you have such different merger rates. So if you were to measure, say, the mass-size relation in the cluster and field environment at a fixed redshift and a fixed stellar mass, you should find that quiescent galaxies are smaller on average because they haven't had the chance to grow via minor mergers compared to field quiescent galaxies. So this idea has actually been around for a while, and this is a selection of some studies that have tried to do this at various redshifts. And you can see that there's basically no consensus. At high redshifts, there's problems that we don't have large enough sample sizes with high enough resolution or signal to noise. And at low redshifts, people tend to use different techniques to analyze the sizes, or they have data sets in very different filters or coming from different telescopes, introducing systematics in their results. So I tried to do this study, but I tried to use a better sample. And this is a sample of 10 clusters at redshift 1, which is part of the G-class survey. And 500 cluster members were identified. And now we have 38 orbits worth of HST Wide Field Camera 3 GRISM follow-up, which is what this whole project is based on. So there are many ways in how this data actually helped this study. The first way is it actually increased our sample size. So this is a plot of spectroscopic versus cluster redshifts and photometric versus cluster redshifts of the G-class quiescent sample. And you can see that there are many redshifts that are consistent with the cluster redshift, but in terms of photometric redshifts, there's no way of telling which of these are secure cluster members and which of these are actually false detections. But with GRISM redshifts, the scenario changes. You get an increase in precision by a factor of 3, and you can see there's a clear separation between these points and these false detections. These are all GRISM cluster members that have a spectroscopic redshift to support their membership. And we can essentially use this increase in precision to select galaxies from our GRISM-only sample that are confident cluster members with 90% confidence. So I've said in general that GRISM spectroscopy helps to increase our sample size. We are going to do the observations, well, we did the observations, the data reduction and the analysis in the same way as our field sample, which is from the 3D HST CANDLE survey. And the quality of our HST data obviously allows for reliable size measurements. So on the left here we have the cluster mass size relation, and on the right we have a field mass size relation. And there are some interesting points. The first is you can see that this region is populated in the clusters and it isn't populated in the field. But what we're more concerned about is measuring the size offset from the quiescent relation of the quiescent galaxies. So we do this for both environments, and then we work out the relative size offset. And what we actually find is quiescent galaxies are about 20% smaller in clusters compared to the field. And if we are to plot this on a plot where we have the average evolution in the size in the field, our result is here. And the magnitude of this size offset is actually consistent with the size of field galaxies between a redshift of 1.2 to 1.5. It also represents the redshift at which most of the mass would have been assembled for the G-class clusters, suggesting that since these galaxies fell into the clusters, their size growth possibly has been inhibited because they haven't had the chance to grow via minor mergers. However, this poses a problem because previous results show that most of the low redshift studies find that there isn't very much difference with environment. So how is it that you have size growth inhibited in cluster environment, but by the low redshift, the cluster environment somehow catches up with the field environment? In clusters, you will have a scenario where quiescent galaxies will build up over time, but the quiescent galaxies that were there at redshift 1 will still be there at redshift 0, suppressing any increase in the intercept of the quiescent mass size relation. And as we saw, we require rapid growth in that to explain the observations. So, if you can't grow them, then you have to destroy them. And there's two ways you can destroy compact quiescent galaxies. You can either merge them with the BCG or tidally disrupt them into the ICL. However, both of these things have constraints on them. So if we are to do a toy model, we have to make sure that we follow these low redshift constraints. So the first thing is that BCGs are found to double their stellar mass between a redshift of 0 and 1, and the ICL stellar mass fraction is between 6 to 23% at low redshift. We also have to make some assumptions. We assume that most of the mergers a BCG will experience are with galaxies that are already in place at redshift 1, and this is a natural consequence of dynamical friction because these galaxies would have had time to sink to the bottom of the potential well. We also assume that ICL is negligible at redshift 1, and considering the low redshift studies, we're going to assume that the stellar mass and size distribution of galaxies in both environments are similar, since the mass size relations are similar. And we can use this last assumption to select an area on the low redshift field mass size relation that is relatively absent of compact quiescent galaxies that we can essentially use on our high redshift clusters to select galaxies that need to be removed by either merging with the BCG or being tidally disrupted into the ICL. And if we do this using the minor mergers prescription of size growth, this is what we get. So in each panel, the gray dots are the BCGs, and the percentage highlights the percentage of compact quiescent galaxies that are added to the BCG, so it grows via the minor mergers hypothesis. And you can see in the 100% scenario, obviously the BCG sizes are ridiculously high compared to what we observe. But if we check what percentage of compact quiescent galaxies are required to merge with their BCGs, such that the BCGs double their stellar mass between a redshift of 1 and 0, we find that it turns out to be 40%. So you can see in the 40% scenario, most of the BCGs also do follow the low redshift stellar mass size relation. However, what this means is that 60% of the compact quiescent galaxies will have to be thrown into the ICL. And we have an ICL constraint that we've got to worry about. So will this actually hold up? What we actually find is you do get an ICL stellar mass fraction that is well within the range observed, suggesting that this could be a viable cluster-specific mechanism by which you can get agreement in the two mass size relations at low redshift without the need for individual growth in quiescent galaxies. So in summary, what processes are happening to reconcile the cluster quiescent mass size relation with the field one? I am suggesting that because you can't grow clustered quiescent galaxies significantly, you can create the rapid growth in the cluster environment by destroying some of the oldest galaxies in the cluster. However, you have this additional process where more galaxies will be added from the field, and these will be larger because they've had the chance to grow via minor mergers. Which brings me to the second idea, which is the idea of recently quenched galaxies. And these are 23 spectroscopically identified recently quenched galaxies in the cluster. And you can see they're basically very boring. You can't really, they're just disks. There's not much interactions going on. We can see where they lie on the mass size relation, and they actually lie here, which is a very distinct region. So it shows that they lie on the large size end of the quiescent distribution, suggesting that they will contribute to increasing the average size in the quiescent population. So I'm going to put a summary of my conclusions up, and I think I'll stop there since I'm running over. Yes. Yeah.
Have you compared simulations trying to figure out what the implications might be?
No, not yet. That's the natural next step. So I spoke to some people in Leiden who are looking at the hydrangea simulations to see a similar thing, but that would be the natural step to look at the dark matter, which I haven't yet.
Any comments or questions?
Yeah.
How constraining is the ICL fraction? What percentages do you get for the 0% case and the 100% case?
Oh, that's a good question. So do you mean like when? Oh, okay. I see what you're saying. I haven't actually checked for the 0 and 100% because we were just more concerned about the case where we removed the galaxies we're more worried about. So I haven't actually checked what percentages you get for the 0 and 100% cases.
Looks like everything was clear. Thank you very much.
Okay, no worries. Sorry.
So I've lost the HDMI cable. There was one here.
Okay, that's weird. Right, here it is.
Nope, that's,
you-
it's the adapter.
Yeah, it's done.
Good afternoon. So I'm visiting from the University of North Carolina, and I'm going to talk to you about the observational signatures of Kination. So I'm a cosmologist, which means I have to start with a timeline of the universe to let you know what era I'm thinking about. So here we are at the cusp of dark energy domination. Before that, there was matter domination. Before that, there was radiation domination. And before that, we think there was a period of inflation. However, there's a gap. We don't know how we got from inflation to radiation domination. All we know for sure is that the universe was radiation dominated at a temperature of about 3 MeV. This is in order to set the stage appropriately for Big Bang nuclear synthesis, which works, so we don't want to mess with it. Now, this means that we're talking about the first 0.08 seconds after the end of inflation. So you might think this is a small gap. But this is how a cosmologist views this gap. The temperature, or the energy scale of inflation is, say, maybe 10 to the 15 GeV. The temperature at the start of BBN is 1 MeV. So we have 18 orders of magnitude in temperature evolution that's completely unaccounted for and inaccessible to observations. This is more cooling than the universe has done since BBN. So from my perspective, this is most of the history of the universe, and this is a major embarrassing gap. This gap is also important because we think that dark matter was produced during this gap. So if we want to understand anything about dark matter and its origins, then we have to understand what happened in the gap. And so how do we think dark matter came about? The dominant idea is that dark matter is a thermal relic. So just a quick review. This means that you start with some hot photons or leptons that pair produce dark matter, which then annihilates back and forth. The photons cool so that pair production stops. Annihilations then continue until the dark matter is diluted so much that the dark matter particles can't find each other anymore. The time between collisions exceeds the age of the universe, and you're left with a relic dark matter density. This is the freeze-out scenario. And somewhat miraculously, you get the right amount of dark matter out at the end if the annihilation cross-section is on the order of 3 × 10 to the minus 26 centimeters cubed per second, which means a lot to the particle physicists because in particle physics units, that's the electroweak scale. This is a weakly interacting massive particle. We all do our victory lap and go home. The problem is that it's actually easier said than done to come up with a real weakly interacting particle that has this cross-section. This cross-section is order of magnitude correct, but it's actually this precise value of it is kind of in a desert of particle physics models, that most particle physics models have cross-sections that are either a little too high or a little too low. So we can widen this field because if we relax the assumption that the universe was radiation dominated during this era, which we obviously don't know for a fact that it was. So what do we know? What happened to the inflaton after inflation? This is the million-dollar question. So during inflation, the inflaton's energy density is dominated by its potential. That's the definition of inflation. Inflation ends when its kinetic energy becomes significant. Now, what can happen then is it can oscillate in the bottom of its potential well. That leads to an effective matter-dominated era. That's what I talked about in the colloquium this morning. Right now, I want to talk about the possibility that it fast rolls. That leads to a period of kination, kinetic energy-dominated expansion after inflation. And this leads to an energy density that redshifts away as 8 to the minus 6. Many people have looked at kination over the years. It's a very attractive idea to try to tie it in with quintessence somehow. So this work is work that's been appeared in 2 papers recently. It's actually led by my graduate student, Kayla Redman, who's graduating this year, but unfortunately does not want to stay in academia. So dark matter production during inflation. Density as a function of scale factor. The kineton is just redshifting away as 8 to the minus 6. Radiation will then naturally become dominant. So this will give a radiation-dominated universe, no decay required. That sets us up for BBN, and that's parameterized by this reheat temperature. Dark matter reaches equilibrium, enters its annihilation phase, and then freezes out. However, it never actually freezes out during kination. There's always this relentless annihilation, which is also seen by some other folks, that leads to a logarithmic decrease in the co-moving abundance. This shows the relic abundance of dark matter as a function of cross-section. And the solid line here is our target point. That's the observed value. The blue line shows the kind of standard value I gave before. And you see that if dark matter freezes out during kination, larger cross-sections are required to get the right relic abundance. That's because the expansion rate during kination at a given temperature is faster than during radiation domination. So the dark matter freezes out earlier, and so you need a larger annihilation cross-section to compensate. The fact that the cross-section is larger than canonical means that this scenario is already strictly constrained by observations looking for indirect detection of dark matter. So these plots show reheat temperature as a function of mass, the major parameters of this scenario. The blue is ruled out by Fermi observations of dwarf spheroidals. The green is ruled out by the Hess observations of the galactic center. The purple is ruled out by unitarity constraints. And anything above the black line is dark matter freezing out during radiation domination and therefore boring. So you can see that there's only like very tiny windows that are left that you could make your favorite dark matter particle work by invoking kination. And so then we looked at perturbation growth during kination to try to see if this could give another handle and maybe close those little windows. And so during kination, this shows the evolution of the fractional density perturbation in dark matter. And we were rather surprised to find that dark matter perturbations actually grow linearly during kination, just like they would during matter domination. This was at least extremely surprising to me when we first saw it, because kination is even, in some ways, it's more pressure than radiation domination. So surely it should be even less growth. And indeed, this growth is not gravitational. The gravitational potential is wiped out because the perturbations in the kineton field don't grow. So the gravitational potential is gone, and yet we still see this growth. And what's happening is the particles are just drifting towards the overdense regions. When they enter the cosmological horizon, they get initial shove towards the overdense regions from gravity, and then gravity, the gravitational potential fluctuations disappear, and then they just continue to drift towards the overdense region. Because of the kinematics of kination, that drift grows linearly, as opposed to logarithmically during radiation domination. So it's the same mechanism that gives you perturbation growth during radiation domination. It's just the expansion rate that gives you linear growth. This linear growth then will lead to an enhancement in the small-scale power spectrum on scales that enter the horizon during kination. And so this shows the density fluctuation as a function of k, and you can see there's a rise at large k, small scales, a deviation from logarithmic growth going to square root k growth. And this in turn leads to an increase in inhomogeneity. So this is sigma m, the density fluctuations in mass m scales. These are Earth masses. These are tiny little microhalos. Normally this is very flat, but if you have a period of kination, it rises up on small scales. And this will lead you to more microhalos, which will boost the annihilation rate and could close that gap. So in summary, I would say that these kination scenarios and the dark matter particles that rely on them are on the edge. Current observations already just leave a very narrow window of allowed space, and that does not include any enhancement due to a boost factor from microhalos. We now know that there is such an enhancement in the microhalo population, and so what we're doing right now is trying to see, is this boost that you would get from this inhomogeneity in the microhalos that result enough to close that gap. Thanks.
What ends this process of the scale? Does the scale of it eventually end up in some vacuum state?
So normally what would happen, so it becomes subdominant just because it's redshifting away faster than radiation. What happens after that is, generally in kination scenarios, the idea is that it reaches a new plateau, begins to slow roll, and it's now dark energy. So that's why kination is a popular way to try to unite inflation with dark energy, kination is a way to dilute the energy density rapidly to take you from inflationary scales down to dark energy scales. So yeah, the major, so then it would just appear like quintessence today. And the only way we could maybe hint it is to see this imprint on the matter power spectrum, a relic of its fast roll phase.
Follow up on this. So would this predict that the expansion was constant throughout the history of the universe, or would that be?
Well, no, because the kineton, the scalar field that does this, would be subdominant for, you still get radiation domination followed by matter domination. So the idea is the kineton's fast rolling and dominant, but it's redshifting away faster than radiation. So eventually then radiation will come to be dominant, and then matter will be dominant. Meanwhile, this scalar field has reached a plateau and is now slow rolling again, giving you a density floor that will be then exposed recently in dark energy domination.
Yeah, I mean that's what I meant, like more recently. Whether you make specific predictions of how W would be changed.
Oh, no more so than any other quintessence model. So just it can be basically a generic. Think of this as just like this first stage of a quintessence model.
So this diagram is interesting. What does LHC add to this story?
Not much. So this is really just looking at annihilation cross-section. And the nice thing about annihilation cross-section is it determines the relic abundance. So all that goes into this is how do we get as much dark matter as we see?
Some of this mass range is ruled out, right?
No, because there's nothing in here that talks about how it talks to the standard model. So this is all about direct annihilation. It does not mean, it's not connected to how easy it is to produce in colliders. So yeah, if you have a specific SUSY model that you want to live right here, then yes, you can ask, is that model constrained by observations? But while there is a relationship between annihilation and production cross-sections, it's at the energies associated with the LHC, it's not a given that just because we can see it annihilate, we should also see it in the LHC.
To me, it seems reasonable that if it annihilates and makes photons that Fermi is supposed to see, then it should go the other way as well in LHC.
Not as
required.
not as required at the energy levels that LHC has. The cross section can be very small.
I see. Okay.
So no, it's not as given. So I mean, a typical particle that would live in here would say be like a Higgs xeno. Higgs xeno normally is not a viable dark matter candidate because it produces too little dark matter. Its annihilation cross-section is too large. This model makes it viable, and there are definitely still SUSY models with the LSP being a Higgs xeno that are still allowed by the LHC. Because really the LHC is then more looking for the squarks than the LHC never had a good job, never was going to be all that great at finding the neutralino. The LHC was really supposed to see squarks by now. Oh, yes, absolutely. But, and I think that is also inspired as kind of broadening the field of dark matter particles.
So in this model, you do not allow light dark matter particles, only like in this white region?
Well, light dark matter particles in this model, lighter than this, so basically, as thermal relics, they're already ruled out by Fermi. So Fermi already rules out in this scenario of even just radiation domination, any thermal relics less than 100 GeV. And so that doesn't change. Kination only makes it worse because it makes the cross-section larger. So if it's a thermal relic, Fermi's already wiped that out, at least down to Fermi's floor that, Fermi can't see much below a few hundred MeV. Don't quote me on that. So below that, then it would just annihilate to something Fermi can't see, and then maybe it's still viable.
No, because I just know that there's many people searching, studying this light dark matter particles as viable.
Well, those are usually the ultralights. So those are usually the more like axions, and they're not thermal relics. They're not thermally generated. They have a different production mechanism.
Okay, so it doesn't speak about that.
Mm-hmm. No, this is assuming that dark matter is thermally produced. Right here.
Am I connected? Yeah, great. Well, delighted that you have taken a chance to ask a historian to come and address you. I guess my job here is to say, do we have any hope of a common language that might be translated into, let's say, something that could be publicly consumable? And you can all imagine that there's good reasons to be publicly consumable. I learned that pretty early in life in my own training, where as a freshman at UCLA, I started at Griffith Observatory, and I said, boy, that's where it's at. So I'm now at the Smithsonian, senior curator, history of astronomy, and I've been there for some 38 years, working on galleries, and we are now going through yet again another gallery renovation. This time the entire building is being renovated, and I will not get into that unless you give me a beer. What we have here is an artist's conception of Explore the Universe, which was first developed in the 90s. It took about 10 years to go through 3 directorships, including my dear friend Martin Harwitt, who got it going. And then by the time the gallery opened in September 12th, 2001, which was a very quiet opening, the museum was being directed by a 4-star general and former assistant commandant of the Air Corps. So, you know, the museum changes drastically, and we've just gone through another significant change, and I will talk about that in a moment. But the question is, and let's see if I do this right, for a gallery that has averaged 4,000 visits a day for the last 18 years, it's a question of what do we do with this gallery in the future. Now, you know, we get anywhere between 7 and 9 million people a year. So that's really only a capture ratio of about 1/3 of the entire museum. And naturally, with one astronomy gallery, or technically 2 if you include the planets, and some people still think that's astronomy, it's not a bad capture ratio. But certainly would like to make it larger and also make it more accessible. Because I must say, in the times that I spend in my gallery looking at these people bumping into the walls and sleeping on the floor, I wonder what kind of message is getting across to them. So, let's see, how's this working? Oh, there we go, okay. We're going to be closing in 2021 and reopen in 2025. The entire building is going through a rolling closure because the building itself is sick. It was built on time and under budget, which means it is incompetent, and we are now paying the price for it. And I, again, will not go through the details. Now, happily, this particular gallery was one that was voted to continue in theme. We are, in the course of this whole process of 7 years, it is called transformation. And one definition of that is anything you had in there was wrong and everything that goes in has to be new and right. Well, we don't all agree with that kind of definition. But let's take a quick look at the gallery as it stands. It's about 5,000 square feet. And in that 5,000 square feet, it's a linear process where you go through looking at what the universe looks like and what do we think about it if we only had our eye to use, then if we had a telescope, then if we added photography to the telescope, then if we added spectroscopy to the telescope, and then finally digital capabilities, both on ground and in space for signal processing and also computation. So this has been a popular gallery. These are the objects that are in it now, the artifacts. You might recognize the Z machine in there, at least listed. And it would be very nice to continue the connections that I've had with people up here who have been very, very involved in developing these. If we were to take a quick tour of the gallery, the overall concept that we had in the 90s was whenever we apply new tools, conceptual or perceptual, to study the universe, we find it isn't what we thought it was. And when we opened in 2001, there was a question about dark matter. You know, at that point, just before that period, we were saying, well, either we have it really very right finally, or it's totally wrong. And we turned out to be totally wrong because the dark matter, being able to, let's say, perceive its presence and think about it, tells us we're in a universe that's completely different than what is normally perceived by electromagnetic radiation. So, how do we get these ideas across using artifacts? We constantly remind ourselves that we are a museum. That means we are a history-related kind of entity. We collect things that validate our history and the existence of certain things that have happened in the past. It's nothing like seeing the object and knowing that it really was used by some particular person who we like to tell a story of as well, that something happened. And I stick to that. But there's a very strong trend in museology these days that is moving away from artifacts to other types of platforms. And this is one of the questions that we're all engaged in at this time. Well, in terms of the revolutions, of course, we have a replica of Tycho's equatorial armillary, which was the instrument that provided the data that Kepler used to show that planets don't travel in circles. And we do show how the Aristotelian universe was eroded. To the point where with Copernicus we have an either-or thing, which system works. The telescope answered that question, so that's the first step. The second step was, is this universe a universe of stars, or a universe of something other than stars, of which the Milky Way as we see it is only one part? The person who asked that question using observations, not philosophically, let's say, like Immanuel Kant or someone, was William Herschel. And so we have the original Herschel 20-foot telescope that he built in the 1780s, along with the last mirror that he built, along with his son, and they both signed, which was kind of cute. And we go through the story of how he and Carolyn, sitting in the window up there, gauged the universe over a period of 25 years, and essentially determined, assuming that the telescope was big enough to see to the end of the universe, that was the assumption he made, that the number of stars and everything, they could determine the construction of the universe, its shape, which they did. But they found that those fuzzy objects that they call nebulae didn't fit that pattern at all. And Herschel was a good enough inquisitor, encouraged by his sister, to be absolutely frank, to say, William, we don't know what they are. They could be solar systems in formation, which was a Laplacian thing to do, but there could also be something totally different. Why is there distribution, and why is my machine driving me crazy? Okay, welcome to the government, by the way. This is a government machine. It won't let me get my... Does anybody know how to use a computer? Help me. Oh, there's a cursor. Okay, my apologies. Come on. Okay, let's continue on. So Herschel asks, what are those nebulae? Hubble answers them equivocally. They are island universes. We are in a universe of galaxies. Well, Hubble had photography to work with. Sure, he had a bigger telescope, but he had photography. And we like to make a big point with our visitors, and we make a big point in there about how photography is better than the eye. The eye doesn't integrate, photography does. And I don't think we have to go through that. We're contemplating a even more intimate interaction. Okay, please don't boo when I tell you, and we're certainly not going to call it this, but this is how we've got the attention of the designers. Okay? I mean, I figure if I can get the attention of the designers by saying something outrageous, then maybe the public will listen, all right? So how are we going to talk about integration? And we're going to create an interactive that is called Expose Yourself. All right? Now, I don't recommend you do that. Please, I don't recommend you do that, and I make a big point of that, but it helps sell and get attention to what the question is. And the length of the exposure will show you in different aspect, different brightnesses, different contrasts, that sort of thing. And we're not going to call it that. We have another one called Guess My Gas, and we're not going to use that, but it gets the attention of the people who we're working with to build these new exhibits and gets them thinking. And that's a very important part of this. So we have Edwin, and he will remain. That is, by the way, the life mask of a senator, the closest to the structure of Edwin. Unfortunately, there's no life mask for Edwin Hubble. Then we move on to spectroscopy. And the instrument that we include here is the original Mills spectrograph from the Lick Observatory. This is a trompe-l'oeil, a very beautiful trompe-l'oeil. That telescope's not in the gallery, but the Mills is. And that is the telescope, the design that was the design that was used by Slipher at Lowell to first determine the recessions, and of course then refined by Hubble with the distance scales to come up with the expanding universe once again. So we now end up, this is a linear process in this gallery, we have a gallery that takes you up to 1960. Galaxies exist, the universe is expanding. What does that mean? In the digital section, we try like anything to represent, let's say, the prediction of the Big Bang from, using the model that Gamow made to celebrate their calculation, prediction of the background radiation. This says ilum there, and that's the Greek substance for the primordial substance. And we juxtapose that with Penzias and Wilson's tracing of the signal from their instrument at Holmdel. And in juxtaposing observation and theory this way, how do we reach our audiences? We have tried various summative evaluations of this kind of juxtaposition, that this was a commemorative device, but it doesn't reveal process, except that it does provide insight to Gamow as to what he considered important in life. But that's not the intent of our gallery. So let me move on. Oh, I keep on hitting the wrong button. The most important thing we do, and that we're going to continue to do, is say that there are no final answers. There are only refined questions, and those refined questions lead to better answers, and the answers lead to better questions. There's no final answers. And to do that, we have a presentation that everybody has voted to keep in the gallery, but maybe using newer technology that actually works. We pose those questions on a wall, and then you can get answers to those questions here and choose what decade you want to get an answer for, starting when it was posed and up to now. And up to now, then we have interns who come in and follow reports from observatories and news reports, trying to get reliable things to see how those answers changed. That has made an impact. We have found that this really works with our audiences. So that will change. That will stay. We have a lot of interactive exhibits that have been ad hoc put into the main exhibit in discovery stations. We roll them in, roll them out. We want to integrate them in the new exhibit. We want to make the discovery stations accessible to our public without our exhibit educators. Even though our exhibit educators, they're undergraduate and high school kids called explainers, and we pay them. We have volunteers. We have all sorts of people. We have about 300 people coming in to do this sort of thing for all of the galleries. It is a vibrant part of our operation, but they can't be there all the time, and so we want to be able to integrate it better. We end up inviting people to observe at the Mayall telescope at Kitt Peak, and they play with them and other instruments here. We want to continue that sort of thing in the future. So that's the gallery as it is now. And ETU is one of the few galleries in the renovation that will remain more or less intact. However, a lot has changed in 20 years in astronomy, in society, in museum practice. So how are we going to change? Well, one thing I want to be able to blend, the very big with the very small. And that is, of course, clearly the direction that a lot of you are going. and we want to learn how to do that better. At first, we decided, okay, no more linear process of discovery. We're going to give the visitor a chance by having a central hub where they come, they get oriented, and then they can decide to see what kind of universe they want to look at, historical or contemporary. Then we went the next step, and this is where we are now, moving the hub to more of a stage, and then asking big questions. What are stars? What are galaxies? Does the universe have a beginning and end? Is that all there is? So on and so forth in there. And so this is a complete change. And I must say it was done by an education staff who are all trained astronomers who came from various places because we got an endowment to build a public observatory, and we gave finally a place for astronomy to live at the Air and Space Museum. Thoughts? I'm hard of hearing. Too many people in the building.
You focused on the physical universe, but a major frontier in astronomy these days is astrobiology. You might want to consider that, exoplanets.
Good question. We have another gallery called Exploring the Planets, and they have completely revolutionized the way they're looking at the solar system.
I'm talking beyond the solar system.
Yes. Typically, you have a gallery on the solar system. You start with the sun and you go out. Now we're going to start in the stars looking at exoplanets and move in to see, is the solar system different than all of those things out there, or are we looking at a universe that's just like us? And they're using, we've got the engineering model from Kepler. That was fun. That was quite a bit of handshaking, but Bill Barucki was really good to us. And so we're going to be centering it on exoplanets. Exactly. But does that follow? I mean, it's not biology. Biology is not allowed in our museum. No, it was in Life in the Universe. We had a Life in the Universe exhibit, which was very interesting back in the 70s, and it was the most controversial exhibit. It had people coming in. We have to be very careful because for them, it's flying saucers. And the way the government acts, you believe they're there, they have to be there. So my apologies, but yes, we do have one curator who is very interested in incorporating some biology, but we have to be very careful.
One quick question, Dan. Yeah, are you thinking about how to incorporate the new field of gravitational waves around me?
Absolutely. I had a little square there that said LIGO. We've just gotten an offer from Caltech, which took about a year and a half, to give us the prototype quadrupole suspension system for the mirrors, laser mirrors. We also have been talking to the laser people about how they built a cleaner laser beam. But, that's it. But how are we going to display it? We don't know. And we're talking to the LIGO people about ideas. How do you, typically what I'd do is I'd create a laser table and show them interference and all of that. I'm not sure that's, one quick thought is to show what's the big success of LIGO is isolation. So we're going to create something where kids can jump up and down and everything vibrates except whatever's on this table.
Why don't you focus on black holes?
Black holes is an amazing fight. There are so many people within the museum who say it is incomprehensible, you can't deal with it, blah, blah, blah. It is hilarious. Have you read Marcia Bartusiak's Black Hole? It's brilliant, and I'm trying to get as many people. First of all, she talks about how resistive everybody has been to black holes all these years.
We have a center here.
You have what?
A center for the Black Hole Initiative, the only center in the world focusing on black holes.
So if I go in, I'll never get there, but I'll never get back? Thank you. Okay.
Thank you.
Are you comfortable with this?
Yes. I figure it out. talking about black holes. I'll try to catch up on some time. My name is Christina Eilers. I'm a PhD student at the Max Planck Institute for Astronomy in Heidelberg. And a question that I've been addressing during my PhD is the question of how do supermassive black holes actually form in the early universe? And the question is interesting because if you look at the most distant, the highest redshift quasars known, at between redshifts of 6 to 7.5, and you look at their central black hole, you can measure it, and you can measure the size of it, and you see that they all host about 1 billion solar mass black holes. And this is at redshifts where the universe is only 700 to about 900 million years old. So less than a giga-year. And still we have these supermassive black holes. If you make certain assumptions about the accretion rate of these objects and about their lifetime of the quasars, so how long they have been shining and growing the black hole, you can calculate back what the initial black hole seed mass must have been by the time it started growing. And then there are certain theories that predict different initial seed mass ranges, basically. And in this case, we assumed that these black holes have been growing throughout the whole Hubble time at the theoretical limit, the Eddington limit. But that might not just be quite right? So probably these black holes didn't start growing at the Big Bang, but maybe a bit later. So if we reduce the quasar lifetime and reduce the time that these black holes had time to grow, basically, you can see how the initial seed mass must have been a lot larger by the time they started growing. So if we turn this around and say if we could actually constrain the lifetime of these objects, the time that these quasars have been growing their black hole, we can then also constrain the black hole formation theories. And people have been trying to constrain quasar lifetimes mainly with quasar clustering studies. And that principle is based on the fact that you have you count the black hole, you count the quasars, and you count the dark matter halos, and the ratio of it basically gives you an idea of the lifetime of quasars. But so far, this method has yielded only very weak constraints, and there's like results between 10 to the 6 to 10 to the 9 years. So it's several orders of magnitude uncertain. And also, it only gives you an idea about the quasar population. So what I did during my PhD is try to figure out a method how we can actually constrain lifetimes a bit more precisely, and also for individual quasars. At these redshifts, the only thing we have accessible is the quasar spectra, and a quasar emits fairly continuous over the whole wavelength range. But while the light from the quasar travels through the intergalactic medium towards us, you get this, you have some remaining neutral gas fraction, gas patches in the IGM, and this causes this dense pattern of absorption lines that you observe in quasar spectra, which is called the Lyman alpha forest. And at redshift 3, this looks roughly like this, but the spectra we're more interested in are the higher redshift quasars that are redshift 6 and higher, and you can see this quantitative difference. And that's due to the fact that the higher you go in age of the universe, so the further away these quasars are, the closer you approach the epoch of ionization, so you have a larger neutral gas fraction, and that causes more absorption in the spectrum. What I did during my PhD is create a new data set, or assemble a new data set of high redshift quasar spectra. And at the moment, it's about 30 spectra between redshifts 5.8 and 6.5. They're all taken with the ESI instrument and the Keck telescope. And most of them come from the archive. Some of them we observed ourselves. And then we reduced all this data homogeneously and co-added the different exposures. So in total, it's about 180 hours of telescope time. These are the spectra. They're publicly available over the IGM Spec database. If you want to work with them, you can just download them or ask me about it. So how now do we get information about the lifetime of these objects from the spectrum? What we do is we run radiative transfer simulations, and just to see how the spectrum of a quasar evolves with lifetime. And what I'm showing you here is the neutral gas fraction of the IGM in the upper panel and the spectrum of these quasars in the lower panel. So if we turn on the quasar, you can see how the quasar starts to ionize the IGM, the gas around it, and creates this ionized bubble. And in this region where you have more ionized gas and less neutral gas, you have more transmitted flux. So the larger this quasar, basically, the longer this quasar shines, the more neutral gas you have around it and the more transmission you can observe. So if we could basically somehow access how much transmitted flux there is close to the quasar, we could get an estimate about their lifetime. And this is the so-called proximity zone measurement. So just briefly, how do we measure proximity zones? We take a continuum normalized quasar spectrum, we smooth it to a resolution of about 20 angstroms in the observed frame, and then we check where the smooth flux drops below a certain threshold. And that's what we say is the size of the proximity zone. And we did that not only for one skewer along in our simulations, but for about 1,000. And this is how this so-called proximity zone measurement evolves with the lifetime of quasars. And you can see there's two regimes, basically. There's an increase here, and then it flattens out. And this is due to the fact that the neutral gas fraction of the IgM evolves with time as a function of the photoionization rate, which is this gamma here, and a function of the recombination rate. And recombination is really long for hydrogen, so we can basically ignore it. So at a certain distance from the quasar, the IgM goes from a fairly neutral state to a fairly ionized state at the characteristic time scale, which we call the equilibration time scale of the gas. So if you go back to this picture here, for short quasar lifetimes, shorter than the equilibration time scale of the gas, you see this dependency of proximity zone versus lifetime, whereas then it flattens out once the gas has reached ionization equilibrium with the quasar's radiation. And then you see this increase here again for very long quasar lifetimes, which is due to the reionization of helium-2. Okay, so going back to the data now. We did measure the proximity zones for all our quasars. This is here the proximity zone on the y-axis now versus the magnitude of these objects. And this gray region is the prediction from these radiative transfer simulations for a fiducial quasar lifetime of 10 to 7 or 10 to 8 years. And you can see it matches actually really well. It's not fit, it matches quite well. However, we do have 3 quasars that show very, very small proximity zones compared to their magnitude. And you can look at them a bit more in detail. These are the spectra. This one is a bit of an exemption because it looks like it has a large zone, but given its magnitude, it's actually also really small. So what's going on with those? I'm going to focus on this middle panel here and go back to this plot that I showed you earlier. If we just look at the spectrum and where the proximity zone, so this is again just the proximity zone measurement, falls here, you can see that it prefers incredibly small lifetimes. So actually this is the distribution, the posterior distribution of lifetimes for this one quasar, and we have them for the other 2 as well. And it prefers quasar lifetimes of 10 to the 4 years or less, and the best estimate actually predicts that the quasar turned on by the time the pyramids in Egypt were being built. So this is actually a bit of an issue, because if you go back to this plot and say, okay, we have one quasar that is about 10 to the 4, predicts about 10 to the 4 years lifetime, 2 more with 10 to the 5 years. Anyway, if you just turn back the lifetime to 10 to the 4, 10 to 5, or even 10 to the 6 years, you can see there's no time for these black holes to grow to the observed sizes. So basically, these initial black hole seeds must have been incredibly massive. So we don't know yet what's going on, but we have a few ideas, and I'm just going to flash them out briefly. If you have any more, I'm happy to more ideas. I'm happy to hear them. At the time t0 today, we observed this quasar, and the question basically is, how did this quasar look like 10 to the 4, 10 to the 5 years ago? One option is that these quasars actually were off. It was a quiescent galaxy. There was no black hole growth happening. This could imply a few things. Either we have very massive initial seeds, maybe from dicollapsed black holes, even though that would just loosen the tension a little bit. But that would be an option. It could be any combination of these, really. We could have super Eddington mass accretion rate. So this theoretical Eddington limit is maybe not quite right for these objects. We could have flickering quasar light curves. What I mean with this is that maybe quiescent galaxy and active quasar phases alternate. So we could have multiple growth phases. That's an option. We could also have a very high merger fraction, but we are talking orders of magnitude here, so it's a bit hard. The other option would be, for example, that that these quasars have been shining and growing their black holes much longer, but we just didn't see it because we have initial dust enshrouded growth phases. That would imply that we have a very, very high fraction of obscure quasars in the high redshift universe, which is much larger, should be much larger than what people predict. It could also imply that maybe these obscure quasars are an evolutionary rather than a geometric phenomenon.
So we don't know yet what's going on. We have an ALMA and a NOEMA program though going on to find more of these young quasars and get an idea of like the abundance rate of these objects, and also maybe whether there's they have a lot of companion galaxies or something like that. So we're trying to figure that out. All right, perfect. I'm just going to conclude quickly. So we developed a new method to constrain quasar lifetimes by measuring the sizes of the proximity zones. We find an unexpected population of very young quasars that challenges the current black hole formation models. It could potentially hint to super Eddington accretion rates or maybe flickering quasar models or anything else really, and we're trying to figure that out at the moment. Thank you.
One other option that you might want to consider is tidal disruption of a star, because that feeds a black hole with actually more than Eddington during the disruption, and that would make it a quasar
For a short amount of time.
Because the amount of fuel is rather limited, and we know that that there are lots of in the early universe, lots of stars in the vicinity of a black hole that would be shredded.
It's basically so you have basically a very high impact merger. Yeah.
Well, we see those tidal disruption
Yeah.
events, and why wouldn't we expect them to be in a small fraction of all the quasars?
It could very well be, yeah, I think. It's a good idea. Yeah.
Yeah, wouldn't the flickering model not work out because the recombination time is so long? So that's kind of why these really short lifetimes are really pretty...
In this case, at redshift 6, the flickering would work out because recombination is very long, but only to get hydrogen back to neutral. And at redshift of 6 or so, we already have a fairly ionized AGM. So you only have to go back to neutral gas fractions of 10 to minus 4 or so to make it opaque for Lyman alpha. However, if you do the same experiment at redshift 7.5 and 7 for the highest redshift quasars, you see an IGM damping wing, and that gives you basically an integrated constraint on, even if it was going on and off, like you can still see the integration of it. And Fred Davies, who's also who's a postdoc in the group that I'm working with, he did that for a redshift 7.5, and he also gets 10 to the 6 years lifetime. So we do have a problem there, and there it can't go on and off, at least. Yeah. No, yeah.
Does the proximity zone, the size of this proximity zone, does it depend on the density of the gas?
It could depend on whether, so if you have basically a damped Lyman alpha system or a Lyman limit system, so a very dense blob of gas in front of it, that could shorten the proximity zone. For these objects, we have very deep optical and near-infrared data, so we can actually look at whether we see like a Lyman limit system or something, and we can rule that out.
No, I meant the density of around the system itself, not if there's another system.
No, so if you have a dense blob of gas in front of it, you would for example, you can look at it would black out completely, not only Lyman alpha, but also the other Lyman series. And we can look at all the Lyman forests, and we do see transmission in the delta forests.
The question was more about the mean density of the gas within, the point is that at 10 megaparsecs, you expect the intergalactic medium to have close to the mean density.
Yeah, okay, so unless you have very, very dense gas for 10 to, 17 or so, then it wouldn't matter. But if you have very dense gas, we can rule out that option actually quite well.
Thank you very much.
Thank you. I don't know how to turn that off.